Hello everyone. While we're all joining this event from our own location, I would like to acknowledge that we are meeting on the lands of the Wurundjeri people and the Bunurong people of the Southeast Kulin Nation. I'd like to pay my respects to their elders, past, present and emerging, and to all First Nations communities joining us today.
Thank you very much for that, Kim. Hello, ladies and gentlemen. Welcome to the first ever virtual night at the Observatory. First things first, some introductions. So I'm Jamie. We've got Kim, who gave us the introduction over there. Thank you, Kim. We've got Andrew. Give us a wave, Andrew. Andrew is our resident tour guide for this evening. We also have Neil over in the corner there. Give us a wave. Thanks, Neil. Neil is our astrophotography expert for the evening. We also have Drew as well. Just to kick things off, I'm just going to give you a little bit of a rundown of how the evening is going to go. We have a Q&A function for the webinar that we're on tonight. So that one is, if you have a look in the bottom, you should have a couple of little speech bubbles there. You can pop in your questions for us. The best ones we will take note of and we'll answer those at the end of the night.
That's for the people who are joining us on Zoom.
Yes. If you're joining us on Facebook, you can send in your questions as well. The best ones will be sent to us as well throughout the night. Just going to give you a little bit of a demonstration of who we are and what we do. So we have a little bit of an introduction, an origin story here, if you like. All right, so just a little bit of a background here. This image was taken at one of our public viewing evenings before our visitors have arrived. So we've got some Dobsonian telescopes there, and we can see the Monash Dome and the Chook Shed in the background there as well. A little bit more on those later on tonight. So just to start us off, Monash University was originally constructed in the early 1970s, was a site for their students to conduct research on. So as you can see here underneath the telescope, the students were primarily focusing their research efforts on variable and binary stars. So for those who don't know, a variable star is a star that has different light levels. These can be periodic. They can be for a variety of reasons, but one of them, which I find really interesting, is that varying light levels can be an indicator of what's called an exoplanet. So that's a planet that orbits around a star that isn't our sun, which is really, really cool. And we're using that in our search for extraterrestrial life. So that's really, really cool. Binary stars, again, for those who may not know, is basically where we have two stars that are in orbit around each other. Bit more physics involved in that one than what I personally understand. But that one, you don't have to have two, or you can have more than two. They don't have to be the same type of star. They don't have to be the same size either, which is really, really cool. And they just orbit around each other as they move throughout the galaxy as well, which is quite cool. So we've got the log cabin as well on the grounds. So that one was constructed a little bit after the main dome, which we now call the Monash Dome. That one provided an area for the students to sleep while they were studying overnight, as well as a kitchen area so they could have dinner and coffee throughout the night. It's got a toilet and a shower area there as well. Just to give them, some sort of living accommodations while they were there all night for possibly weeks on end. MBO, as it stands now, took over the lease back in 2011. So next year will be our 10-year anniversary, which is really, really cool. Since we took over the lease, we've maintained, repaired, and even put in some upgrades on the site. So now we are a working museum. So this is just a picture here of what the site looked like when it was first constructed. So this is in the mid-1970s, not long after the log cabin was built. You can see that a little bit of that one off to the right-hand side there. We've got the main dome, or the Monash Dome, off to the left as well. A bit of a different view there these days. There's a fair few more trees there now than what there was back in the 1970s. Doesn't hinder us too much though, which is good. So just another image there of the Monash Dome. And this is the grounds now. So we've got a smaller dome in the back there. That one is called the Celestron Dome. I'll explain a little bit more on that one later on. We've got the chook shed in the middle. Again, more information on that one to come. We can see the Monash Dome there, standing proud in the middle there. We've got the log cabin towards the bottom of the picture. And we also have a dam, as you can see on the left-hand side there. That one isn't our property, but we have lots of duck friends that like to sit in there and come and visit us from time to time, which is nice. So just another shot here, and you'll notice that we've got some red lights on the driveway there. Now, astronomers use red light for a very specific reason, and that is because it doesn't interfere with your night vision. So red light uses different receptors in your eyes. So we've got cones and rods, and the cones are primarily used for color interpretation, and we need white light for those ones to work. While the rods are for just different light, and they're not impacted by red light, which is why we use that one. So this is just a photo of the log cabin as it is now. So this is where the Monash University students would have had their sleeping accommodations. There were bunk beds in this area there as well. Since we've taken over, we have converted it into a clubhouse, if you like. So we have our members' nights there usually, and we have a bit of a projector at the back there as well, so we can have presentations and things we hold in there as well. We've got our library at the back there. Kim is actually our librarian. So Kim has done an amazing job of cataloguing and organising all of the books in the library. One of the perks of membership is that you can borrow any of these books that we have in our library. Just take it up with Kim. And if you have any more questions on that side of things, we'll answer them throughout the night. So this one is an external shot of the log cabin. With our path that we've put in fairly recently as well. We've got the chook shed off to the right hand side. A little bit more on that at the moment. And as you can see, we've got some more trees in there now, a few more than what we had in the 1970s, but they give us oxygen. So can't really interfere and be too annoyed with them interfering with our view too much. So just a little bit of a peek here into the inside of the Monash Dome. You can see in the middle of the opening of the roof there, you can see the 18-inch telescope, just a snippet of that one. That one is, I'm not going to use the word new, but that one isn't the original telescope that was in there. I'll explain a bit more on that one later on. So here's another shot of the Monash Dome with the roof open. You can see again, we've got some red lights in there as well, because when we have things like public viewings or we have members' nights as well, we can be in there for extended periods of time. So we don't want to be using white light and ruining our night vision. So this here is the plaque that is on the outside of the Monash Dome. This one says Monash University Observatory. So this observatory was established to provide an observing site for the 40-centimetre telescope purchased from the estate of the late Mr. L. Jeffrey of Bendigo in 1968 and commissioned in the observatory university workshops. The observatory building, which was designed and fabricated by university staff, was erected in 1972. The log cabin, providing observers' quarters and a display centre, was erected by university staff in 1975 with generous financial assistance from the William Buckland Foundation. The bottom one there, just says, if you can read that, just says modifications to the telescope and dome completed in 1984. So that one was when we had our new telescope installed in that one. A little bit more on that one later on, but for now I want to talk to you a little bit about the Celestron Dome. So this is the smaller dome that you would have seen in one of the earlier photos that I showed you. So this one is a relatively new installation. This one was put together back in 2017. And this one houses a smaller telescope than what is in the Monash Dome. This one is a Celestron telescope, hence the name Celestron Dome. This one is a 14-inch telescope. All that means is that the mirror that's at the back of the telescope, if you can see my cursor here towards this section here where we put the eyepieces in, just the black bit there with the handle, that one, the mirror is at the back there, and that's just 14 inches across. So the size of the mirror determines how much light we can collect, which influences how far and how faint the objects are that we can see. This is the chook shed. So the chook shed is still a bit of a work in progress. That one was put in around the same time as the log cabin. And that one is going to be used, once it's finished up, it's going to be used as an astrophotography centre. So that one is where members can come up and take photos themselves, or they can learn from our astrophotography coordinator, Neil. All right, so this here is the original telescope. So as you would have seen from the plaque, this one was purchased from the deceased estate of Mr. L. Jeffrey back in 1968. This one was a bit smaller than the one that's in there now. This one was 16 inches across. So remember, the mirror that's at the back of that one was 16 inches. This one held all of the scientific instruments that they were using for their research at the time, but due to wood fluctuating with the heat, so expanding as it gets warmer and contracting, as it gets colder, and the weight of the instruments, the university actually retired this one. So this one, this is just another angle of that one. So the instruments here, that you can see that they were using these for spectroscopy in their research on variable and binary stars. So spectroscopy, in a nutshell, is just identifying what objects are present in astronomical objects based on their spectra, or light absorption and emission lines. So this is just an example of the type of images that they were taking with that one. So this is a spectrograph of the sun. And if you were a scientist, you'd know the absorption lines there are indicative of various elements that are present within the sun, primarily hydrogen and helium, which the sun is burning to produce light and heat. So you can see here is just another photo of the original telescope. We've got a big white bar off from the bottom right hand corner. That one is actually in line with the Earth's axis, so it's tilted at the same degree as the Earth's axis, and that one is to make sure that it is easier for us to find various objects based on their coordinates in the sky. Not going to go into too much detail on that one, but it also means that we can track objects in the sky throughout the night. So there is some equipment there in the Monash Dome that we use for using the telescope to track objects throughout the night, and Monash University students use that technology as well, and it just meant that they could track the same object throughout the night, the same object that they were doing their research on. So jump forward to the present day. This is the telescope that's in there now. So this is the newer one. This is the one that Monash University replaced the wooden one with. So this one's a little bit bigger. This one's an 18-inch telescope, so it's got an 18-inch mirror at the back. It's about 45 centimeters. And this one has a metal tube on it, which has a couple of advantages over a wooden one. It means that it's not going to fluctuate with the heat. And it also means that it is able to support the weight of the scientific instruments that the university had attached to it. Those instruments aren't actually hooked up to that telescope there. We've got some weights there on the bottom of the handle there. And that one was just to make sure that the telescope is correctly balanced. So it means that it can hold its position relatively well without anyone having to hold onto it all the time. All right, so what we do now, so we do a variety of things. We run outreach events just like this one. So we have public viewing nights or nights at the observatory. We have scouts and school groups come up to visit us as well. We also run our astrophotography program, as I've mentioned. For those who don't know, astrophotography, like the name suggests, is taking photos of the night sky. We also have a radio astronomy program. So essentially that one is listening to the sounds of the universe. Believe it or not, the universe is actually saying a lot. And we use different radios and things to listen to those sounds and record them and make various observations. A couple of other examples of outreach programs that we've been involved in. We participated in the Avalon Air Show back in 2018. We were invited by the Victorian government for that one to come and participate and show off what we do as a community organisation. We were also involved with ScienceWorks in creating the Astrolight Festival, which was a huge success while we were running it. But after a couple of years, we developed some different goals. So we split off and we've been moving in a different direction from that one. And we were also a movie set for the movie The Comet Kids, which was released back in 2017. Some of you may have seen that one. And if you have, you'll have noticed that a couple of the scenes in that one were actually filmed in the Monash Dome, which is really, really cool. So that's our another one of our claims to fame. So that's it from me. Thank you very much. And yeah, enjoy the rest of the evening.
Yeah, so this is Neil. Before we see your doco, can you tell us what made you want to join Mount Burnett Observatory?
Oh, well, I've always been interested in space and science ever since I was a kid. I love looking at the stars and learning about the planets. About 8 years ago, I moved into the Dandenong Ranges. And after living there for a couple of years, I discovered that we actually have an observatory here in the hills. And I had no idea about that. I'd never heard of it before. So I went along to the open day just to see what it was all about. And I was amazed. So many cool people, so many cool things. Joined up on the spot, and I haven't looked back since. So I really love my time with my fellow astronomy nerds, getting to do cool things with cool people. So yeah, it's a lot of fun.
Fantastic. Thank you. So what are you showing us tonight?
So yeah, I have put together a short series of mini documentaries that we're going to be looking at. I'm going to play them in between the other speakers' talks. And they're just short sort of information bites about different topics in astronomy. So they are going to be something that will be an ongoing theme throughout this series of lectures. So over time, you can build up a little bit more knowledge and understanding of the universe. And the first one we're going to start with is, what is a nebula?
A nebula is a vast cloud of gas and dust in space. After the Big Bang, the entire universe was sparsely filled with hydrogen and helium gas. Much of that eventually condensed into stars and galaxies, but a lot of it still remains spread out between the stars. In the billions of years since the Big Bang, stars have been born, live and die. When stars die, a great deal of their mass is spread through space nearby after great shedding events or catastrophic explosions called supernovae. This spreads more of the gas and dust back into interstellar space. Today, when we look deep into the night sky, we can see a lot of this dust lit up by the stars nearby. Nebulae get their colour from the stars, either by reflecting the star or being energized by their light so much that they glow like a fluorescent light. By studying the light from nebulae, scientists have learned much about the history of the universe and the life cycle of stars. And professional and amateur astrophotographers have created many beautiful images for us to enjoy.
Well, wasn't that interesting? Thank you very much for that one, Neil. I'm going to hand over to Drew now. I've got a little bit of a similar style of talk about the Earth. Drew, all yours.
Okay, so I will get Neil's assistance to fire this up. This will be the first of a series of short and sharp presentations that hopefully you enjoy. Welcome to the first of a series of short presentations. This one is about the Earth, which of course is the planet on which we live. Now the Earth spins on its axis, which runs between the North Pole in the Arctic, meaning where the bears are, and the South Pole in the Antarctic, meaning where there are no bears. Directly above the North Pole in the sky is the North Celestial Pole, and directly above the South Pole is the South Celestial Pole. More on that later. Around the middle runs the equator. And due to the rotation of the Earth, it bulges slightly at the equator. It's round, but it's not perfectly circular. Now the Earth rotates from west to east, which makes everything else, relatively, appear to move from east to west, rising in the east and setting in the west. Let's look at that in action. Now the amount of time the Earth takes to rotate on its axis is a day. However, there's actually two slightly different sorts of day. To do a full 360 is a type period called a sidereal day, meaning a day relative to the stars. But the angles of the sun and the Earth make the sun take slightly longer, and it takes a solar day, which is what we generally refer to when we refer to a day and how we measure our time. Now, I mentioned the South Celestial Pole before, and if you're in the Southern Hemisphere like me, and you go out on a clear night, you can see the stars appear to move around the South Celestial Pole, just like this, but it takes a little bit longer, so it does take a little bit of patience. Now, thank you for attending this presentation. There will be more presentations and videos throughout the night, and we look forward to answering your questions at the end of the evening.
Well, I, for one, am certainly going to remember the distinction between the North and South Pole. The North Pole has bears, the South Pole, no bears. Great way to remember. If ever you get confused, just remember that one. Thank you very much for that one, Drew. Kim, I believe you have another question.
Drew, while you're still there, what's your favourite astronomical object or event? Do you have one?
That's a very good question. There are lots of events like total eclipses and things that are really spectacular to watch, but I have one object that is by far my favourite, and that is Jupiter, the king of the planets.
Pretty
And hopefully we'll
spectacular.
hear more about Jupiter shortly.
Okay, I've got more from you, Neil.
What exactly are you wishing upon? The solar system is a messy place, full of rocks and dust and planets and stuff. The solar system was originally a cloud of gas and dust. Over a long time, that all started to clump together to form the sun, planets, asteroids, comets, and more. But an awful lot of dust remains. A shooting star is a fragment of dust or small pebbles entering the atmosphere of the Earth. For billions of years, it has been orbiting the sun until one day its path intersected with the Earth and it was game over. For stuff to stay in orbit and not fall towards the sun, it needs to have always been moving very fast, so that when the pebble hits the atmosphere, it hits it hard. So hard that it generates incredible heat and almost instantly melts away, leaving nothing but a bright flash and ionized gas. It's the flash of it burning up that you see as a shooting star, a meteor. Most meteors are tiny, smaller than a poppy seed. Larger ones burn up more brightly, what we would call a fireball. These can be up to the size of a walnut. When they are bigger than that, however, they have a chance of actually surviving re-entry long enough to make it to the ground. Then they are called meteorites, rocks from space. You can even buy a meteorite of your own. It will be the oldest thing you ever touch, since they have remained mostly unchanged since the birth of the solar system 4.5 billion years ago.
We've just got one short message now from our supporters, our sponsors, and that is you guys. We've got something in special for you that you might find interesting.
Mount Burnett Observatory is funded entirely through member efforts. So if you enjoy astronomy, would like to help support us, and score yourself some cool gear, you might be interested in the MBO Supporter Pack. In this pack, you'll get yourself an MBO branded t-shirt and warm beanie to help protect your head on the cold nights, as well as a red light torch, essential equipment for preserving your night vision when observing the stars. You can get all of these items together for $49.95 Australian on our website. Together, that's a saving of more than $20, and shipping is free within Australia. So head over to our site, pick up a pack, and show your love for the observatory.
All right, thank you very much. Back to you, Kim.
I think we've got Andrew next, don't we, Jamie?
That's correct. Andrew, over to you.
No worries. And good evening all. Tonight I'm going to take you on a trip, and somebody mentioned Jupiter. There we are. Now, we couldn't just have you all running outside and still be able to see your screen, so we've put the sky on the screen for you. This is a application called Redshift, and they've kindly allowed us to use that tonight and to show you people what's happening. Of course, you won't see those lines, you won't see names in the sky, but this is the sky as it would be tonight, right now, at 7:59 p.m. and 21 seconds above Melbourne. And even if there's no clouds like there is on the screen, it's much better out there, of course, if you can have a look. And I want you to promise me right now that when this program is finished, you will go outside, and I hope it's clear enough, you will have a look into the sky, have a look and see what we're talking about here tonight. It's really something else. Up here, almost directly above us right now, is the star of our show tonight, Jupiter. There it is. And right next door, you will see another, what appears to be a star, which is Saturn. Jupiter's got a yellow tinge to it, and it's about the brightest object, except for the moon, which is somewhere over to the right there. That's quite bright tonight as well, but Jupiter's the second brightest object in the sky at the moment. Saturn's just next to it, and if you're lucky enough to have a telescope, you can see some wonderful things having a look at these planets. Let's just zoom in a little bit on Jupiter now, center it, and let's just have a closer look. As we get in, you'll see 4 more lights will appear. If you can actually see these through binoculars if you've got them, if you hold them steady. Those 4 bright lights next to Jupiter are its 4 Galilean moons. Now, Jupiter's actually got, at last count, 79 moons. But these are the 4 you can see quite clearly through a telescope or just a small telescope or some binoculars. You can also see bands of colour across the planet. In particular, tonight, you're very fortunate because right now, one of the best known features of Jupiter is visible. There it is right there. It's actually been going across the planet for the last couple of hours, but fortunately, it's just about to move off. There it is there, and it's what's called the red spot, or the Great Red Spot. The red spot's been visible for hundreds of years. We don't still really know exactly what it is. Our best guess at the moment is that it's a giant anticyclone. It's a giant storm spinning anti-clockwise. We'll have a closer look at it later. That's what you'd see if you had a powerful enough telescope. Wouldn't be that sharp. You wouldn't see all that detail. Mainly you'd see those bands of colour across it. But we've got the benefit of technology. So let's just zoom back and you can get another idea of where it is in the sky. It's actually quite close to the constellation known as Sagittarius. All right, there's Sagittarius. And Sagittarius is our guide towards the centre of the Milky Way as well, our own galaxy. So how are we going to get a better look at it? Well, let's go there, all right? Let's not just look through a telescope. We'll get away from Earth's atmosphere, away from Earth itself. Climb on our rocket ship and away we go. Let's go to Jupiter. Planets and moons, there we go. All right, and away we go now. Of course, it takes a lot longer than this to get to Jupiter in the real world. Having a look as we circle around the planet now, there's the dark side. It won't be long before it's the light side. Jupiter spins quite rapidly, actually, once every 9 hours and 55 minutes. So really spinning quite quickly, twice as fast as the Earth. And you can see this is not a distorted picture. Jupiter is quite noticeably wider at the equator than it is between the poles. And that's due to that very high spinning rate. It spins faster than any other planet. Now, let's have a look again. We just move back a little from the planet. And sure enough, there are the Galilean moons again. The closest one is Io. The next one is Europa. Then comes Ganymede and Callisto. Now, at the moment, they don't look too far off what they really are, but of course, they're circulating around the planet. If we just go hang on, come in here. Let's go above it and you might get an idea as well. Here we are looking down on the North Pole, and that gives you a better idea of where those moons are. There's Io, closest in, Europa, the next one around, Ganymede, and Callisto. It gives you a better idea of just how far they are from the moon. When we're looking from Earth, we get the illusion that they are closer or further from the planet just by the way they are in line with the planet. Let's have a closer look at one of those, really important one. Let's have a look at Io. Io is one of the most amazing moons of all. Let's zoom in. There's Io. All right, now we're looking at it from above, but even there you can see it's quite spectacular. Io's surface is changing all the time. It's never constant. One of the most amazing things that was discovered when the Voyager spacecraft went there, back in the 1977, the Voyager spacecraft headed off on what they called the Grand Tour, which was going to visit as many planets as possible because they all lined up in a nice pattern across the solar system. And one of the most amazing things they discovered, and I think it was Voyager 2, was an actual erupting volcano as the space probe went past Io. And that volcano was spewing matter 400 kilometres above the planet. It was quite spectacular and one of the most amazing discoveries ever made. It was spewing lava, just like volcanoes on Earth, but a large part of that is also sulfur. And that's why we get that colours that we do on Io. Sulfur can be yellow, red, different shades in between, depending on how long it's been there and so on. But basically, it's still lava that comes out. Now, how can something that far away from the sun be hot enough to spew volcanoes? Well, it's not the heat of the sun that does the job, nor is it just the heat of the pressure within the planet that might cause some of Earth's volcanoes. Io is trapped between Jupiter, the largest planet in the solar system, and 3 of the largest moons in the solar system, all of them, exerting strong gravitational forces, and they are twisting and warping and pulling Io apart almost, and all that twisting and warping generates lots of heat. And as a result of that, we get very high temperatures within Io and continuous volcanic action. Hundreds of volcanoes going off all the time. And that's why the surface is changing all the time. There are virtually no meteor craters on Io. It's all volcanic. All right, let's zoom back out and take another look at the planet itself. There we are. There's Jupiter. Let's get it back in the center. Okay, zoom in and let's go back around to the front again. We are talking about the red spot. Okay, so let's have a closer look in. Oh no, the red spot's disappeared. Help. Oh, there it is. Ah, look at that. There we go. There's the red spot. Now that's huge. Now the planet itself is how wide? Well, it's 633 million kilometres away from us. It's huge. To give you an idea how huge it is, that red spot, as shown there, would hold 2 Earths. It's a little bit of a misrepresentation because the red spot apparently over the years has been shrinking. It was 3 times as big when it was first observed about 200 or 300 years ago, but over the last century, it's gradually been shrinking. There have been other spots actually appearing instead, and some of those have become permanent as well. But the red spot's still huge, and the Earth would fit inside that. It's spinning around and around in an anti-clockwise direction, and like a storm, except we're used to cyclonic storms. On Jupiter, this is an anti-cyclonic storm. These bands of colour, let's just go out a bit, and let's go around the front again. These bands of colour represent zones of winds that are blowing in opposite directions to each other. You can probably get that effect with these layers here. And those winds are going at hundreds of kilometres per hour in opposite directions. The planet is really, really turbulent. In fact, of course, we're looking at the upper atmosphere. The whole planet itself is mainly hydrogen and helium, but some of this stuff is ammonia and ammonium hydrocarbon, which gives us that white cloudiness. There can be a small amount of ice crystals there. There's a bit of sulfur and phosphorus and methane and a few other things as well, that when the sun's UV light falls on the planet, gives us those sorts of colours. So quite a fascinating planet. It's got a huge magnetic field. The magnetic field is in fact 14 times stronger than the magnetic field on the Earth.
That's amazing, Andrew. How would we go walking on Jupiter?
I think you'd have a lot of trouble. In fact, the surface, as you would call it, doesn't really exist. There is apparently a kind of a transition from gas to liquid, and you have to go, in fact, thousands of kilometres in before you strike anything that might be solid. And the problem is that then there's a couple of things. One, the pressure would crush you. Two, the temperature builds up towards 30 or 40,000 degrees centigrade. And three, your own head would crush you due to the increase in gravitational force. So I don't think I'll be volunteering to do that. In fact, some of the space probes that were purposely sent into Jupiter to measure those sorts of things weren't just melted, they apparently were vaporized, and certainly don't exist anymore. Short of time, right? So let's back away from the planet and let's go back to Earth. Here we are, heading back. You can see the sun and the other planets. And here we are arriving back on Earth. Perth's now had the sun go down, and down we come back in somebody's paddock. So thank you for that. Next time, hopefully, we'll take you to Mars, if you can want to look forward to that.
Look forward to that, Andrew. Thank you.
No worries. All right.
What is your favourite thing about Mount Burnett Observatory?
I think two things. What I'm doing now more than anything, I used to be a teacher and I missed that a bit. So being part of the outreach team is really enjoyable. They're lovely people and I've learned a lot more than I already knew. And the other thing is I get to play with amazing telescopes up at Mount Burnett. I've got my own in the background, but I really enjoy using the telescopes up at Mount Burnett as well. So thank you.
Thanks, Andrew.
Less than a century ago, our universe was much, much smaller. Astronomers had long observed spiral and elliptical nebulae, but weren't entirely sure what they were. In the early 20th century, Edwin Hubble, using a technique developed by Henrietta Leavitt, discovered that galaxies were actually millions of light years away, and not part of the Milky Way as had been thought up until then. A galaxy is an immense island of billions of stars travelling through mostly empty space. Galaxies can take many forms, from the classic spiral to barred spiral, elliptical, lenticular, and irregular. Like everything else in the universe, they are in constant motion, and their huge gravity can cause them to collide and combine, creating bizarre but beautiful shapes. Our own galaxy, the Milky Way, is understood to be a barred spiral galaxy with tightly wound arms, more than 100,000 light years across. The solar system is about 2/3 of the way to the edge in an otherwise unremarkable region of space. If you go out on a dark night, especially in the middle of winter or summer, you can see the faint river of light arching across the night. You aren't looking up at the sky, you're looking out into the galaxy. Hi folks, I hope you're enjoying this evening's stream. Coming up next, we've got your questions and answers, but before that, Here are a few important messages. This series is made possible by a grant from Cardinia Shire Council. Thank you to the Council for that. If you like what you see here and you'd like to see more, you can follow us on our social media accounts. You can see the addresses on your screen now, including Facebook, Instagram, and our website. If you love astronomy and think you'd enjoy being part of our community, you might want to consider becoming a member. Memberships are $50 per person and cheaper for families, and you can sign up on our website mbo.org.au. Members get access to all our digital content, including recordings of past and future speakers at members' nights, special digital-only content, and access to the recordings of these live streams. In addition, you get voting rights at our annual general meeting, and once we can go back up to the observatory, you'll have access to all the facilities we have for members there, including special interest groups, telescopes for borrowing, and lots more. So if this sounds like something for you, or a great gift that you'd purchase for a friend or family member, check it out on our website mbo.org.au. If membership isn't your thing, we're currently working on building a digital subscriber service for people interested in astronomy who want to get access to lots of cool digital stuff. Keep an eye open for more news on that coming in the next few weeks. Don't forget, this is a monthly series, so if you'd like to be notified when the next stream is going live, then follow us on our Facebook, Mount Burnett Observatory Incorporated, and you'll get notifications when we create new events. I'd also like to thank all the people involved in creating this series, including our president, James, the event coordinators, Kim and Jamie, our speakers, Andrew, Drew, and myself, Neil. Technical support from Paul and Anthony, and other support from Heike and Stuart. A variety of Creative Commons music was used throughout this stream. You can see the credits for the music used on your screen now. Now, let's hear your questions and get some answers.
Well, as Neil said, we hope you're enjoying the evening so far. Just like to give a welcome to Stuart, who is joining us for the question and answers. Stuart is a current PhD student. He's doing a degree in astrophysics. So we should have some high-level knowledge helping you with answering your questions tonight. So just going to kick us off with one about what defines a nebula. I believe Drew would like to add on to the information from Neil's documentary earlier this evening.
Yes, I think Neil answered it quite well in that first doco that we saw. A nebula is in fact a cloud of dust and gas, and in many of the nebula you get stars forming. But I'd just like to add one little bit of trivia to that. There is a thing in the Northern Hemisphere sky called Andromeda, and it was called the Andromeda Nebula because it looked like all the other nebula in the sky. It wasn't until people looked very closely at it that they discovered, hold on, that's not a nebula, that's actually a galaxy like our own. So there you go.
Okay, we have another question. This one's come from Nick. Do meteors have different names, or is it just comets that have names?
I can take that one. Meteors are what we call transient objects. Well, they're very, very transient. They only last for a few seconds or even less. Comets, however, they are transient in that they come and leave Earth in their orbits, but they persist. They stay around a long time, many billions of years. So traditionally, a comet is named after its discoverer, and that is the only name you're allowed to give to a comet. However, meteors, when they hit the ground, if they become meteorites and if they're a sufficient size, then they get names. So one of the famous ones in Australia is the Murchison meteorite, and that told us an awful lot about space. We learnt a lot of new things from studying that meteorite, and it was quite substantial in size, and it broke up into many, many pieces. So it's been spread out across a whole lot of different research institutions and museums. So short answer, meteors don't get names. If they reach the ground and they're big enough, they probably will get names, but by then they're a meteorite. And comets are all named, and they're usually named for their discoverer.
Thanks for that one, Neil. I got a question here for Andrew. Liam is asking you if the great red spot will ever shrink until it disappears.
Okay, well, no one knows the answer for sure, but it does seem likely. It's gradually been shrinking. Apparently, some people have the impression that it has rallied a little bit in the recent past, but generally over the 300 years or so it's been there, it's become smaller and smaller. However, there are other spots waiting in the wings. There are a couple more spots that have become permanent, and apparently white spots combine to form red spots. And that's happened a few times. So there are some replacement red spots on the way, even if this one looks like it may fade out. Another 100 years or so.
Okay.
So it might, but we might not be around to see it.
Now, I have one probably for Andrew as well, since you took us on such a great tour of Jupiter. This one's from Minnie. How old is Jupiter?
Well, as far as we know, Jupiter was formed at the same time as all the other planets. The sun's been around for, I believe, 4.5 billion years. I think probably Drew and Neil can back me up on that.
That's correct.
And the planets were formed shortly after the sun, I believe, when there was some sort of astronomical disturbance which stretched a lot of the material from the sun out into a disk, an accretion disk as it's called, and the planets sort of condensed and took up material as they circled around. The bigger lumps gained smaller lumps until they became the prominent lumps going around the sun, which we now call the planets. And the biggest of all was Jupiter. And Jupiter has an advantage, though. It's probably getting bigger than the other planets as we speak because it's got more gravity than all the other planets. So it's not going to shrink anytime soon. In fact, we saw a comet hit Jupiter just a few years ago. Some of you may know about Comet Shoemaker-Levy.
Jupiter is known as the vacuum cleaner of the solar system. It sucks up any comet that gets too close to it. And thank goodness for that too, because if Jupiter didn't exist, then it's quite possible that the Earth would have been bombarded for a lot longer than it was, and life may not have been able to get a foothold in the light of all that cometary stuff hitting the surface of the Earth. So we owe Jupiter our existence, I think.
Well, it would certainly be a shame if we weren't here to give you this presentation, wouldn't it, Neil? Drew, we're talking a lot about your favourite planet now. Jeff has a question. I believe you might be able to answer this one. Could Jupiter, with its great mass and a high composition of both hydrogen and helium, ever become a new star?
That's a great question. And if I were to give a very not great answer, I would say yes and no. The reason I would say that is that when Jupiter formed, like all the other planets, it was a big ball of gas. And big balls of gas like that can become stars. However, for a cloud of gas like that to become a star, it actually has to be a lot bigger than Jupiter is. So if Jupiter was, I think it's like 1,000 times bigger, it would have become a star, and we would have had 2 stars in our system.
Only
a binary star system. Only 1,000 times. When we're talking astronomical numbers, that's not quite as extreme as it sounds. But were it bigger, we would have 2 stars in our system, which people thought initially was a really strange thing. But it was actually discovered that binary stars are very common, and single star systems like ours are actually quite rare. So we're either very lucky or very unlucky as that goes. But yes, if Jupiter was much bigger, it could have become a star.
As an amateur astronomer, I'm going to take the very lucky, because if we had 2 stars, we would have much fewer nights.
I have a question here from Cherie that is probably for you, Neil, as our chief astrophotographer. How do you take good photos of the night sky?
Well, it's very simple to master the basics, but it's challenging to master it long term, to get a good feel of how to deal with all the different problems you can face. In a nutshell, the short answer: any sort of camera that's newer than 5 years, any digital SLR or mirrorless camera or anything along those lines that's newer than 5 years old will do a great job. You need to get yourself a sturdy tripod. You can use like a cheap department store one. That'll do the job, but you'll probably get frustrated with being wobbly. So the bigger, heavier, sturdier tripod you can get, the better. Put your camera settings on 30 seconds, which is usually the maximum shutter speed. Your aperture at the widest that the lens will do, which is usually 3.5 or 2.8 or something like that. If you don't know what these numbers are I'm talking about, best to have a read up of your camera manual. And change your ISO to around about 1600 to 3200. That's a good place to get started. And you may find that it looks too bright if you're shooting under light pollution, in which case you will need to drop your ISO so that you don't overexpose everything. But ideally, you want to get away from the city and shoot without light pollution. That is the number one thing that you can do to improve your astrophotography. Forget about buying a more expensive camera or buying a new lens. If you have the option to go out into the country and get away from the lights of the city, that is going to have a much bigger impact on how good your photos look than anything else. Of course, once you start getting great results, then you dive down that rabbit hole of wanting to get more expensive gear and more expensive lenses, and they are worthwhile doing. But the most important and the cheapest thing you can do is get away from the city. So use those settings, do a lot of trial and experimentation, and you'll get some results. And if I may just do a little plug here, I did a talk at Mount Bennett Observatory a few years ago about getting started in astrophotography. I recorded that and it's actually online, and that will go into the detail that I don't have time to do now.
Thanks, Neil.
All right, got another question here. This one seems like it's up your alley, Stuart. From Bonnie, could our galaxy collide with another galaxy?
Yes. Yeah, galaxies are flying around everywhere. And if you wait around for a few billion years, then our galaxy will collide with the other largest galaxy in our local group of galaxies, which is the Andromeda Galaxy. So yeah, in a few billion years, we'll collide with the Andromeda Galaxy and become an even large galaxy. But yeah, galaxies are colliding all the time. It's how they evolve and grow bigger, an integral part of their life cycle and of the life cycle of star formation. And it all gets very complicated when you get down to it. But yeah, galaxies collide all the time. And we've got a bunch of dwarf galaxies around our galaxy right now as well, including the Magellanic Clouds, which are slowly being ripped up and absorbed into our galaxy as well. So it's very dynamic out there if you look on the scale of billions of years, of course.
So what does that mean for us, Stuart? Would Earth survive?
I'm not sure if Earth would survive up until the billions of years it would take to get to the point where the galaxies are colliding. We've got a lot of things that might stop us before then, but the actual collision probably won't be that dangerous for the Earth or the solar system, because we think the Earth is pretty large, we think the Sun is pretty large, but the distances between stars within the galaxy is immense. So although the galaxies look like very large objects to us when we look out the sky, when they collide and mess around with each other, it's very unlikely that stars will actually hit each other because there's so much space in between, so they'll just fly by them. Where the real collisions happen is where all the dust and gas is. All the dust and gas of the different galaxies will collide, and then you get what's called a starburst, because there's a huge growth in the amount of stars produced when galaxies collide, and produces these beautiful pictures that you can see from the Hubble and everything else.
Thank you. I have a question from Nicola. It's directed to Andrew, but Drew, you'd probably be able to help with this one as well. How did they know that the space probe vaporized on Jupiter? How were they watching?
It takes about at the moment 35 minutes for light to get from here to Jupiter, or from Jupiter to here. So yes, it is quite a difficult thing, but the space probes that have been there, particularly the Galileo space probe and Juno space probes, they are much more advanced than the old Voyagers were, even though the Voyagers are still going. So they could communicate with huge radio telescopes back on Earth who pick up the signal, and they can tell people back on Earth what the temperature is around them, what the pressure is around them. There are all sorts of sensors on the probe. And the probe was sending these messages back as long as it could, until, of course, all the wiring melted. And then they knew that because the way the temperature was increasing, if it continued to do so at that rate, it would reach a temperature that would evaporate all of the components of that space probe.
Thank you.
That
What a
makes
way
a
to
lot of
go,
sense
hey?
to me.
That's good.
I don't know about you, but I'd like to keep my 2 feet on Earth where they belong. All right.
Yeah, at the moment,
Well,
Mars is looking pretty good right now.
well, I'm sure Andrew will tell us all about that one next time.
I hope so.
But for now, we have a question from Glenn. This one seems like it will be right up your alley again, Stuart. What is Jupiter's gravitational force?
Just a quick look up on the academic source known as Wikipedia. The mass of Jupiter is 300 times Earth, and it's the mass of a planet, which gives it the strength of its gravity. But of course, another way to look at it is that Jupiter is also larger than the Earth, and when you're further away, gravity is weaker. So on the surface, the so-called surface of Jupiter, the top of the clouds, surface gravity is rated at 2.5 times that of Earth. So if you were somehow standing on the top clouds of Jupiter, you'd still weigh 2.5 more than you do on Earth.
Okay, thank you. I've got a question for Robert. I think this one's a great one for you, Jamie. Why is the Running Chicken Nebula called the Running Chicken Nebula?
Well, astronomers are inherently great at naming things. We like to name things based on how they look. So the Running Chicken Nebula looked a little bit like a running chicken. We have another one, which is a prime example, the Tarantula Nebula, which you may have seen in the pre-roll that we had before we started our main presentations for the evening. That one looks like a tarantula, hence the name. Essentially, we're great at naming things. We name them based on what they look like.
I think actually we're alternatively great and terrible, especially when it comes to naming telescopes. We have the VLA, the Very Large Array. We have the Very Large Telescope. We have, there was a few others that I can't think of right now, but they're very obvious, redundant, simple names. So astronomers seem to be at both ends of the spectrum when it comes to naming things.
We just like to keep it simple. Just keep it simple. Just name it how it is. Then everybody knows what you're talking about, and everyone can visualize what you're talking about as well, because it's what it is.
That's right.
Different amounts of imagination involved with these things. Orion the Hunter, if you have him pointed out, you can tell it's a picture of a man up there in the sky. Scorpius, the constellation, definitely looks like a scorpion, but I'm sure Nia will back me up on this. Sagittarius looks absolutely nothing like an archer to me. It just looks like a teapot.
It's a teapot. There's no question about it. It's a teapot.
It's a teapot.
Yeah. Next, we'll show you what the teapot looks like next time, folks.
All right, speaking of next time, unfortunately, that is all the time we have for this evening. If your question didn't get answered tonight, feel free to send it through or hang on to it for next time. Pop it in the Q&A when you join us and we will hopefully get to it then. But for now, thank you all so much for joining us tonight. We hope you have enjoyed the evening, and send us your feedback as well. Drop us a message on Facebook, Twitter or Instagram, or send us an email through our website, mbo.org.au. Until then, stay looking up.